In this problem, I'm going to take up the quiz problem. The quiz problem was given a binary tree. So I had a binary tree, okay, and so let's say that's my root node, and I have a left node over here. I have a right node, and let's just have one more level of nodes here, okay. All right. Let's say this is given this binary tree here. Given this binary tree here, okay, and let's give some values here. Remember, this is not a binary search tree yet. It's just an arbitrary binary tree. So I'm just going to give up some values here. Let's make this 5. Let's make this 3. Let's give this 2, 1, 8, and 7. Okay, so given a binary tree, which is let's call this by a variable, a reference t. T is a binary tree, is a reference that is pointing at this binary tree, where again, just to make this clear, we're using the nodes and references representation of my binary tree, meaning this the root of this tree is referred to by the root node. Okay, you may want to look at my class definition within the binary tree. I forget whether it's root node or it's root, but let's just call this root here. And the left portion of my tree, meaning this entire left portion of my tree, is referred to by left. Okay, let's just keep it simple, left. And whatever is the right portion of my tree, meaning this piece over here, is referred to by right. Okay, again, what does this mean? It means that given this tree T to start with, if I say T dot root, I'm going to get back this, I'm going to get back, in this case, I either get back the node that contains the element phi, but we are going to make a slight simplification here. We're going to assume that root itself is an integer. So t dot root is going to give you back the value phi. Okay, it's going to give you back this value phi there. What does t dot left give you? Well, t dot left is going to give you another tree, is going to give you another binary tree right there. This is another binary tree right here. This entire thing over here is another binary tree. Okay, so this is going to be t dot left is basically a reference pointing at this left binary tree, and t dot right is a reference pointing at the right binary tree. Okay, so what was the problem of the quiz? The problem of the quiz was, given this arbitrary binary tree, sum up every single value in this binary tree, such that you're going to return back to me at the end of the day an integer, which is, it is going to be 5 plus 3 plus 2 plus 1 plus 8 plus 7. All right, so whatever the arithmetic summation of this thing is, you're going to give me back that value. Okay, so how would I write this function here that happens to be recursive in nature? So let's write a function def, and let's just start off my Python's function here, def, and let's call this binary tree sum. And what will this method take in as an input? As an input is going to take in the nodes and references representation of my tree. So let's pass in some t. Okay, now let's do this. Let's just think about the base case here. The base case here is, whatever this tree is, if the tree is empty to begin with, meaning if t is none. If t is none, what is the summation? What is the summation of every single element in an empty tree? It's just going to be 0. I'm just going to say 0. Return 0. If t is not none, meaning t is basically some kind of a tree. Okay, in that case, I'm just going to say return back the summation of the left part of the tree, whatever is the summation of the left part of the tree. Okay, I'm just kind of zooming out of the whole problem here, and I'm looking at it from a very intuitive point of view, saying that the summation of this tree, which is this piece of 5 plus 3 plus 2 plus 1 plus 8 plus 7, this entire thing can be simplified. In something of this kind here. This is the summation. If this is the summation of the entire tree t to begin with, okay, if the sum of this t is this entire thing, I can rewrite this in a recursive nature, which is completely equivalent to saying sum of t is nothing but, how do I get hold of this 5 here? How do I get hold of that 5 there? I just said to get hold of that 5, I must say t dot root. So can I say t dot root? Okay, get hold of that 5 plus sum up the entire left piece of the tree. What is that method that will sum up the entire left piece of the tree? Well, this is the method right there. If sum takes in as an input, if as an input it takes in some t, which is a binary tree, I'm just going to invoke the same method again, which is going to be on t dot left. Okay, and then how do I compute every single item in the right hand side of my tree, the right child of my tree? I'm going to invoke the same method again, but now in place of t, I'm going to pass in the right child of t, meaning it's going to be sum t dot right. But this raises an interesting question. What if t is none? If t is none, I'm going to say none dot left. This is going to result in a none type error. But I don't have to worry about that case because my base case has already checked for that. My base case right there is making sure that if t is none, return back a 0. Otherwise, if t at this point is not none, t at this point is not none. So what should it return back? It should just return back this entire thing. Okay, so let's just formulate that. To formulate that, I'm going to say t dot root. Okay, whatever t dot root is, which is right this piece. Okay, plus whatever the summation of this entire thing is. But remember, my method over here is called binary tree sum, right? So I'm just going to make sure I'm consistent with my methods here. So it's going to be binary tree sum. And this is going to compute everything that happens to be the t dot left portion of my tree, which is t dot left plus binary tree sum, and this is going to be the right hand portion of my tree there. Remember this, the type of this entire thing is an integer. The type of this entire method right there is something that takes in a tree. A tree gets fed into this method right there, t dot left, and the output of that is going to be another integer, okay, which is the integer of every single thing in my left hand side, which is 3 plus 8 plus 1. Okay, so think about this. Think about if this is my root node, which is 5. This entire piece is going to give you back 3 plus 1 plus 8. And you can do that by calling this recursively. If you would like to draw the entire stack trace, I highly encourage you to do that to figure out that this and actually gives you back 3 plus 1 plus 8. This piece over here is going to give you back, this is going to give you back 2 plus 7. Okay, so 2 plus 7 plus 3 plus 1 plus 8 plus 5 is going to give you this piece right there, or is completely equivalent to this piece right here. Okay, so this again, just to recap, this is my base case, and this piece over here is my recursive case. All right, so I hope this was useful, and I hope to see you guys again in my next